Article 445.13 of the National Electrical Code specifically addresses the ampacity requirements for conductors connected to a generator. This article mandates that the conductors running from the generator to the first overcurrent protective device, or OPT, must have an ampacity that is not less than 115% of the generator's nameplate current rating. There is an exception to this rule, allowing for 100% ampacity in specific cases, but the general rule is 115%. This requirement is in place to ensure that the conductors can safely handle the potential load from the generator, accounting for factors such as harmonics, temperature variations, and other operational conditions. The TAP rule, specifically referenced as 240.21, is a provision within the National Electrical Code that allows for conductors to be tapped from a larger feeder conductor, provided that certain conditions are met. One of the key conditions of the TAP rule is that the TAP conductors must have an ampacity of not less than 1/3, or approximately 0.33, of the rating of the overcurrent protective device protecting the larger feeder. This rule is designed to allow for flexibility in electrical installations, enabling smaller conductors to be used in certain situations where the load is non-controlled. However, the TAP rule cannot be applied to generator feeds. Article 445.13 provides a specific and more stringent requirement for generator conductors. The 115% ampacity requirement takes precedence over the TAP rule. The reason for this is that generators can have unique operating characteristics and potential fault current contributions that are not always fully accounted for by the general TAP rule provisions. Applying the TAP rule to a generator feed could potentially result in undersized conductors, which could lead to overheating, insulation damage, and even fire hazards. The code prioritizes safety and reliability in generator installations by requiring a higher ampacity rating for the conductors. The 115% rule in Article 445.13 is intended to provide an additional safety margin to accommodate these potential issues. To further elaborate on the difference between the general TAP rule and the specific requirements for generator feeds, it is essential to understand the underlying principles and considerations that govern each. The general TAP rule, as outlined in 240.21, is based on the premise that the overcurrent protection device at the origin of the feeder provides adequate protection for the entire circuit, including the TAP conductors. The 1/3 ampacity requirement ensures that the TAP conductors can safely carry the load they are intended to serve, while also providing a level of protection against overloads and short circuits. The TAP rule also includes limitations on the length of the TAP conductors, the location of the TAP, and other factors that are designed to mitigate the risks associated with using smaller conductors. In contrast, the requirements for generator feeds, as specified in 445.13, are based on the unique characteristics of generators and the potential hazards they can pose. Generators can produce voltage and frequency fluctuations, harmonic distortion, and other electrical phenomena that can stress conductors and equipment. They can also contribute significant fault current during short-circuit conditions, which can exceed the interrupting capacity of some overcurrent protective devices. The 115% ampacity requirement for generator conductors is intended to address these potential issues by providing a larger margin of safety. The conductors are sized to handle the generator's full output current, plus an additional buffer to accommodate any unexpected surges or variations. In addition to the ampacity requirements, Article 445 of the National Electrical Code also includes other provisions related to generator installations, such as grounding, disconnecting means, and location requirements. These provisions are all designed to ensure that generators are installed and operated safely and reliably. When working with generators, it is crucial to consult the latest edition of the National Electrical Code and any applicable local codes or regulations. It is also important to follow the manufacturer's instructions for the generator and any associated equipment. Ignoring these codes can result in unsafe installations, equipment damage, and even legal repercussions. Here are some additional points to consider regarding generator feeds and TAP rules. 1. the exception mentioned in 445.13, which allows for 100% ampacity under certain conditions, typically involves generators that are specifically designed and tested to operate at a lower ampacity rating. These generators are often equipped with special controls and protection devices that ensure safe operation. However, it is crucial to verify that the generator meets all of the requirements for the exception before applying it. 2. The overcurrent protective device at the origin of the generator feed must be carefully selected to provide adequate protection for the conductors and the generator itself. The OCT should be sized based on the ampacity of the conductors and the generator's short circuit withstand rating. It should also be a type that is suitable for use with generators, such as a molded case circuit breaker with a high interrupting capacity. 3. The grounding of the generator is another critical aspect of the installation. The National Electrical Code requires that generators be grounded in accordance with specific rules, depending on the type of generator and the application. Proper grounding helps to prevent electrical shock hazards and ensures that the generator operates safely and reliably. 4. The disconnecting means for the generator must be readily accessible and clearly labeled. This allows for quick and easy shutdown of the generator in case of an emergency or for maintenance purposes. The disconnecting means should be located in a place where it is not likely to be obstructed or damaged. 5. The location of the generator is also important. Generators should be located in well-ventilated areas to prevent overheating. They should also be protected from the elements such as rain and snow. Generators should not be installed in hazardous locations such as areas where flammable materials are stored. Understanding the difference between the general tap rule and the specific requirements for generator feeds is essential for electrical professionals and anyone working with generator installations. By following the National Electrical Code and other applicable standards, it is possible to ensure that generators are installed and operated safely and reliably. Remember that electrical work can be dangerous and should only be performed by qualified individuals. If you are not comfortable working with electricity, it is best to hire a licensed electrician. Furthermore, the interaction between Article 445.13 and other relevant sections of the NEC is crucial to understand for safe and compliant generator installations. Consider Article 700, Emergency Systems, which might apply if the generator is intended to provide backup power during outages. Article 700 has its own set of requirements for wiring, overcurrent protection, and transfer equipment. These requirements may further influence the selection and installation of conductors and OCTs. Similarly, Article 701 legally required standby systems, and Article 702 optional standby systems outline specific rules depending on the criticality of the load being served by the generator. Each article dictates specific maintenance, testing, and operational requirements that impact the overall system design. The type of load connected to the generator is also a significant factor. For example, if the generator is supplying power to nonlinear loads such as variable frequency drives or electronic equipment, the conductors may need to be oversized to account for harmonic currents. Harmonic currents can cause overheating and premature failure of conductors and equipment. In such cases, it might be necessary to increase the conductor size beyond the 115% requirement of 445.13. Another consideration is the ambient temperature in which the conductors are installed. High ambient temperatures can reduce the ampacity of conductors, which may necessitate using larger conductors or applying dilating factors. The National Electrical Code provides tables and guidelines for adjusting conductor ampacity based on ambient temperature. The length of the conductor run from the generator to the first OCT can also affect the conductor size. Long conductor runs can result in voltage drop, which can reduce the performance of the connected equipment. In such cases, it might be necessary to increase the conductor size to compensate for voltage drop. The National Electrical Code provides formulas and guidelines for calculating voltage drop. The type of conductor insulation used can also affect the conductor size. Different types of insulation have different temperature ratings which can affect the ampacity of the conductor. The National Electrical Code provides tables and guidelines for determining the ampacity of conductors based on the insulation type. The method of installation can also affect the conductor size. Conductors installed in conduit or cable trays may have a lower ampacity than conductors installed in free air. The National Electrical Code provides tables and guidelines for adjusting conductor ampacity based on the method of installation. The presence of other conductors in the same raceway or cable tray can also affect the conductor size. The National Electrical Code provides tables and guidelines for adjusting conductor ampacity based on the number of conductors in a raceway or cable tray. The generator's short-circuit current rating is another crucial factor to consider. The OCP must have an interrupting capacity that is equal to or greater than the generator's short-circuit current rating. Otherwise, the OCP may not be able to safely interrupt a short-circuit fault. The generator manufacturer can provide the generator's short-circuit current rating. Finally, it is essential to coordinate the OCP with the generator's protective devices. The OCP should be selected to trip before the generator's protective devices, such as the overspeed shutdown or the overvoltage protection, to prevent damage to the generator. The generator manufacturer can provide information on the generator's protective devices. In summary, while 445.13 establishes the minimum ampacity requirements for generator conductors, a comprehensive design considers all applicable NEC articles, the specific characteristics of the generator and connected loads, environmental factors, and coordination of protective devices. Failing to account for these factors can lead to unsafe or unreliable generator installation. Always consult with a qualified electrical engineer or electrician to ensure compliance with all applicable codes and standards. Also, proper documentation is essential for generator installations. Maintain detailed records of all calculations, conductor sizes, OCP ratings, and other relevant information. This documentation will be helpful for future maintenance, troubleshooting, and inspections.